It's my great honor here today to introduce Dr. Kate Rychert, a distinguished seismologist, and she got her bachelor degree from from University of Boston, and then she pursued her PhD and master degree from University of Brown. Then she worked as a postdoc at Scripps and worked at the University of Bristol. Following that, she joined the University of Southampton and worked as a lecturer there and got tenure. And now she is an associate professor at University of Southampton. And now she also joined the WHOI and as an associate scientist with tenure there. Dr. Kate is a great seismologist, and especially she is interested in using the seismology method to investigate the lithosphere and asthenosphere boundary. And today here, and she will talk about her recent research about using, the seismology method to investigate the dynamic lithosphere and asthenosphere boundary. So here is yours, Kate.
Okay, great. Thanks for that really nice introduction. Okay. Yeah. Okay. Does that work?
Yep, looks great.
Great. Okay, thanks. Yeah, thanks very much. And thanks very much for inviting me. I'm really sorry that I can't be there today, but I'm still really excited to talk to you about the lithosphere-asthenosphere boundary. So the title of my talk is A Dynamic Lithosphere-asthenosphere Boundary Dictated by Variations in Melt Generation and Migration. I'm going to focus on the PyLab experiment, or passive imaging of lithosphere-asthenosphere boundary experiment, but then put that into a global perspective, considering other works. I'd like to thank especially my co-authors, in particular the several students and postdocs from the PyLab experiment, including Saya Theramina, Shengguo Wang, Petros Bogiatsis, Matthew Agdias, David Schlapphorst, Kostas Liptogaropoulos, Utpal Saikia, and many more. And then also the long list of authors who have currently been working on the global compilations with, in particular, two students, Yuhong Dai and Sinan Ozayedin. Okay. So the notion of a rigid tectonic plate that moves coherently over a weaker convecting asthenosphere is central to plate tectonic theory. However, there's some difficulties in terms of imaging this boundary and knowing exactly what depths it occurs at, and some ambiguities and some conflicts. In the classic geophysical definition of the lithosphere, we think of it as thermal, so colder temperatures at the surface of the Earth result in a more rigid lithosphere. We expect the lithosphere to cool conductively in a lithosphere, whereas it cools, heat transfer occurs by advection in the asthenosphere, and so the transition would occur at the geotherm adiabat intersection, the predicted kind of temperature profiles for those two types of cooling. Before I get into the controversies, I just wanted to remind you why it's really important. Because it's such a fundamental part of plate tectonic theory, it obviously has implications for things like mantle dynamics and our understanding of the interior of the planet. But it also has implications for things like the origin and evolution of the continents, the driving forces of plate tectonics, and natural disasters like volcanoes, tsunamis, and earthquakes, given that they're caused by plate tectonic processes. It also has implications for our understanding of things such as climate change and Earth's habitability. Okay, so the ocean lithosphere is probably the ideal place to study the tectonic plate because of its relatively simple and short history. If it is defined thermally, we expect that the lithosphere would get colder and also thicker with age. And we can image this using surface waves, for instance, since shear wave velocities have a sensitivity to temperature. And so in age bins, you can see on the left-hand side, I'm showing you SE-MUM2 model, just averaged by age. And you can see that, yes, we actually see velocities that get faster and also extend to deeper depths beneath older lithosphere. That's great because that's what we expect for a thermal model. That means that to first order, temperature is dictating the lithospheric thickness. And if it is defined thermally, we also expect a gradual transition in temperatures with depth. So for instance, I'm showing you here some experimental predictions from Fowle and Jackson showing that, beneath younger lithosphere, you have slower seismic velocities, and then you get faster as you move towards older lithosphere, and those faster velocities extend to deeper depths. So again, temperature playing a first order role. However, we now have this host of observations from scattered waves. These are body wave phases that have either reflected or converted at sharp seismic discontinuities. And these observations, shown by the symbols here, also show evidence for thickening of the lithospheric plate with age. Here I'm just showing observations from normal lithosphere, unaffected by hotspots. And on the bottom, you can see I have the hotspot affected regions in red. And you can see that the hotspots, there's a fair amount of scatter even without hotspots, but with hotspots, you get even more scatter. And on the background, I'm just showing you predicted viscosity contours from numerical modeling on the top. And you can see that they agree, we get this sharp decrease in viscosity where we see these observations. And then they also seem to agree in general with predictions from, I'm showing the half-space cooling model for the cooling of the plate in the gray dashed lines, and the plate model as the black solid line. So pretty good agreement with those predictions as well. And also the mildly hydrated solidi, which are in cyan and pink. However, these observations all require a discontinuity that's quite sharp. Something much more like this black dashed line. And so, the degree of scatter is also not predicted by a purely thermal model, and also this kind of very sharp nature of this discontinuity, which is much different than predictions, requires greater complexity. Okay, it's not just scattered waves that requires factors besides temperature alone. There are many, many other observations, and these include things like a very slow seismic velocities. For instance, here I'm showing the melt experiment, and also very high conductivities. So for instance, this example from 9 North on the right. Okay, many subsolidus possibilities have been proposed to explain these observations, in particular, those from scattered waves requiring a sharp discontinuity. These include things like a change in anisotropy, the oxidation state of the mantle, elastically accommodated grain boundary sliding, or in other words, enhanced effects of hydration on seismic waves, and near solidus conditions, or having an enhanced effect on seismic waves. And these are all kind of things that would not necessarily affect the viscosity of the mantle, and therefore make the scattered wave observations unrelated to the lithosphere-asthenosphere boundary. I'm not going to go through each one of these one by one, but it turns out that each of these has been proposed to explain, one set of observations in one location, but these all have difficulty explaining all of the observations from all of the different methodologies, since they have different sensitivities to Earth's properties. So an attractive option is a small amount of partial melt, since that it can easily explain observations from a wide variety of observations. If there is melt in the kind of the percentages that we require it to explain our observations, it likely affects the viscosity of the mantle. And so we'd like to know where it is and what form it's in, so we can better understand mantle dynamics. However, it has been proposed to exist in many different forms. For instance, it may exist as a thin layer beneath a permeability boundary. It may exist in these complex melt matrix structures, as suggested by numerical modeling. It could exist over this entire melt triangle region here, which is something more like that proposed by surface wave models, or something in a very, very thin near vertical channels, I mean, like this area here, which is consistent with this kind of much smaller conductivity anomaly. It may exist in layered structures as proposed by receiver function imaging, and it may fall off gradually with depth, as in this classic transect study, or it may have a very sharp base. So we'd like to know more about that. Unfortunately, a lot of these proposed styles of melt that from various observations come from a single set of observables or a single location, and there's not often a range of methodologies and resolutions and sensitivities in the same location. And so our idea was to use a host of different resolutions, sensitivities, and all in one location, and also to study the Atlantic which is a slower spreading center, rather than the typical, much more typically studied Pacific, which is a faster spreading center, and the Atlantic, slower spreading. The processes are proposed to be quite different, although constraints are rare. And so this was the PyLab experiment, which was a year-long deployment from March 2016 to 2017. You can see here the stations are arranged in 3 lines around the chain fracture zone here. The 2 southern lines cross 2 different ridge segments here and here, and those are the lines I'll be focusing on today. Okay, there were 39 ocean bottom seismometers and 39 magnetotelluric instruments that were co-located. There was also a host of marine geophysical data that was collected, including gravity, magnetics, and swath, and there was an active source component. And this is not just PyLab, this is also Eurolab, Ka Lab, Transatlantic iLab, and several others. Okay, so just going to start right off with surface waves. These are waves that travel across the surface of the Earth, and I'm just showing you here that we have very good ray path density. Okay, so this is our first result. So at shallow depths, here I'm showing 26 kilometers, we see slow velocities beneath the ridges, and that's good, that's what we expect. And we find faster velocities beneath older age lithosphere, again, what we expect for a thermal model. We can also see this in cross-section here with slower velocities beneath the ridge. This is the northern line here, and faster velocities beneath older lithosphere. And also in the south, you can see, again, we have slower velocities beneath the ridge and faster velocities at older ages. At deeper depths, 78 kilometers, we find punctuated anomalies that are several hundred kilometers off axis. And we can also see this in the cross-section. Again, these punctuated anomalies not necessarily located directly beneath the ridge axis. We also find evidence for a lithospheric drip, which was really exciting and unexpected. This is like quite different than what you image, for instance, in the faster spreading Pacific. Okay, so moving on, we also performed receiver functions. These are waves that have converted at a relatively sharp discontinuity and give you an idea of Earth's discontinuity structure. Okay, so at shallow depths, we image a MOHO. It increases from about 4 kilometers to 8 kilometers across the region, and it generally has agreement with observations from gravity, where we find the higher anomalies beneath the thinner crust. Okay, moving to deeper depths and also into cross-section view. Here I'm showing you a profile from the south. And again, you can see the MOHO is imaged all the way across that region. We also see this beautiful LAB phase that increases from about 30 kilometers beneath the ridge to about 70 or 80 kilometers beneath older lithosphere. That's beautiful. It's exactly what we wanted to image, and we were very excited. We just wanted to, go home after that. And you can see also this beautiful age progression here on the western side in map view. Okay. But fortunately, there are complications. That's good. It means we have something to talk about. So on the right, you can see that there's just the LAB is just imaged in kind of this one blip. But that blip does occur just over the slowest velocities from surface waves. So promising and interesting, and we'll talk about the reasons why or why not we might image the LAB in some locations and not others. I also would like to point out that the active source experiment found a beautiful LAB phase at exactly the same depths in this location where we have our simple and straightforward LAB. So that means that this discontinuity occurs over less than 1 kilometer depth, so really sharp. Okay, so again, just looking at both cross sections, although we might not like to, we have the simple case in the southwest. Here on the right, left, I'm showing that it's kind of an undulating LAB character, and not all of it is significant from 0. One thing you might remember is that we had those surface wave anomalies, and those are contoured here. And they kind of suggest a pretty strong topography. And one reason we might be seeing kind of more complex LAB topography and also not imaging the LAB significantly in all cases is because SCP receiver functions have difficulty imaging sharp topography. Another thing that we looked at was P to S receiver functions. We're looking at them now, the mantle transition zone, so 400 and 600, around 400 to 600 kilometers depth. And what we found here is that we found thinning, subtle thinning on the western side of our study area. So this was unexpected as well. We typically don't think of ridges as having a contribution from the lower mantle. But what was interesting is when we compared our result to global tomography models, it was very clear that the velocities were significantly slower beneath the mid-Atlantic ridge, not necessarily all ridges, in comparison to older aged oceanic lithosphere. So that was really interesting to us. And I guess I point this out here because it could be that we have this thinning, and the reason it's probably thinning, by the way, on the western side, rather than being directly centered on the ridge, is because we have this long offset transform, the Romanche, just north of our study region. So in other words, kind of like splitting the difference between the two. So we have this kind of sluggish upwelling. It's not unlike a hotspot, but it's occurring on the western side of our study area, and it could be supplying a constant amount of upwelling and also probably decompression melting to that western side of our study area. And that could be the reason that we see such a simple structure on that side in comparison to the east, which may be less well fed by upwellings. Okay. Moving on and bringing in the magnetotellurics. Okay, so here we have the northern profile and the southern profile, and I have the resistivity values in the background. The surface waves are contoured in black, surface wave velocities, and the receiver functions, where they're significant from 0, are shown in purple. And what you can see is that there's pretty good agreement with the notion that there's punctuated anomalies. We see these also in the MT. The MT also finds higher resistivities near the lithosphere, so that's really great. We have the receiver function phase here above some of the stronger anomalies, and then here where we have this kind of gradual drop off in conductivity with depth. So that's quite interesting. We notice here, this is brand new now. This was not in any of the other imaging, but we have this beautiful channel at near LAB depths. So that was really exciting to us. We wondered why we were only imaging it, in one kind of location in their receiver functions, and we didn't expect to image it in surface waves since it's really kind of a very small feature, and surface waves typically have these much smoother regularizations. Okay, so we did some resolution tests to investigate why the MT might image these things and not the other methodologies. And you can see here that MT is able to resolve punctuated anomalies and also thin channel structures. So that was really promising. And we also did some receiver function testing to show that, as you get thinner and thinner channels, the phase that's converted from the top of the channel is predicted to interfere with the phase from the bottom of the channel. And you can quite rapidly start to lose amplitude to a place where your phase might be too small to observe over the noise. So that's probably why we're only imaging it in kind of one location, but not the entire channel because of destructive interference. Okay, so in summary, things are coming together, but we wanted to see if we could do any better. And so this is what we did. We tried to find bring the surface wave model into better agreement with the resistivity model. The reason that we went in that direction is because the surface waves are strongly affected by the starting model, whereas resistivity has less effect on the final result. And so we took a half-space cooling model shown here in the temperature plot, and we translated it using experimental relationships to shear wave velocities from surface waves and to resistivity shown on the bottom. And we plotted that up. And this is what we got in black here for a purely thermal model. And then we also tried to put in a small amount of partial melt with a small amount of water. And you can see those in the brown and yellow dots here. And that's not really linear, but horseshoes and hand grenades, there's going to be scattered in our data anyways. We just drew a line through it. And you can see that in gray. Okay, so when we did that, and then you can see that line, which I just drew, and compared it to our results. You can see those in the black. I'm plotting here shear velocity versus resistivity. And you can see that, we're doing pretty well. Actually, this histogram is centered on this linear expectation for the relationship between the shear velocities and the surface waves. Not bad. Okay, so we proceeded. We then reparameterized the surface wave model because it was done on a kind of a coarser grid, and we wanted to be able to incorporate these finer scale structures from the resistivity. And so the new shear wave velocity from surface waves is shown on the top for the northern and southern profiles. We then made the MT model translate to seismic velocity using that relationship I just showed you. And then that's our new starting model for the shear wave velocity inversion shown in the middle here. And then we re-inverted for shear velocities using that starting model. And that's the result shown on the bottom. And so that's quite cool. It seems to be in much better agreement. You can see the punctuated anomalies are really coming out. The lithosphere is also this beautiful blue layer here, and the drip is really coming out. And then notice in the south that we have this beautiful channel feature. So this model, I really want to point out, this model fits the phase velocity data just as well as the original surface wave model that I showed you. So surface waves do not mind having this very thin channel. They just wouldn't necessarily resolve it unless they knew that it was there. So that was quite exciting. So it's probably the world's first thin LEB channel from surface waves. Okay, so then we took our new shear velocities and plotted them against resistivity, shown here. And that's shown in the background. You can see that the correlation between them is better, so that's great. And then we plotted these expectations from experiments again. Here I'm showing a purely thermal model in black. And then predictions for more amounts of melt as you move from pink to purple to brown, and then more amounts of hydration in the melt, which is primarily the MT has the primary sensitivity to, as you go from right to left. And then you can take those predicted values and try to relate them back to Earth's properties. And so this is what we get. On the bottom, I'm showing you the predicted temperature field in these anomalous regions. And then I'm showing you the melt fraction in the top panel. We have melt fractions that are mostly moderate, but are up to around 4%. And then I'm showing you the amount of hydration in the melt in the middle panel. And the hydration was probably the most shocking thing. We require some kind of like percentage that's, like an order of magnitude greater than is ever observed at the surface in rock samples. So that was kind of alarming to us, but it's what we got. Then we also thought, well, what else could it be? It could be a small amount of CO2 or a lot of sulfide melt or some combination of these. So basically, we're still trying to figure out exactly why the hydration contents are so high. One possibility is that what's down in the mantle does not necessarily make it out of the mantle. Another possibility is that this is an artifact of resolution. Most of the hydration contents come from the resistivity values, and the resistivity inversion was done on 2 cross-section lines rather than a 3D model. And so in the future, or actually currently, Shengguo Wang, who did this, the MT work, is re-inverting, but it requires doing, and he's doing an inversion of the entire Atlantic, including the basin structure. And so that should help us understand whether or not this is an artifact of that 2D assumption. Okay, so I showed you this great agreement. I'm now showing you on the right-hand side that how good the agreement is. The resistivity values here are now contoured in black, and the shear velocities are in the background, and of course the receiver functions are in the purple lines. And there is really striking agreement between them, but of course we nudge them together, right? Like, so we admit that, of course, we wanted to do a better job, but yes, we're kind of prescribing that we do a better job. But that being said, it's not true that MT and shear velocity always agree, and actually many studies they kind of really don't agree. So the fact that we could do this is actually very promising. The other really exciting thing is the body wave tomography, and that's shown on the left. You can see the velocities in background colors, and the resistivity is contoured on top of that. And you can see there's really great agreement in terms of the idea that there are punctuated anomalies. There's evidence for this lithospheric drip. And then the most exciting thing was that this channel feature is not an artifact, because from this very independent data set, we have this beautiful channel in the shear velocity structure. And so it gives us really good confidence that that channel is there, and the punctuated anomalies are also there. Okay. So I've talked about these kind of punctuated anomalies and channel features, and we've talked about how a lot of these things like sharp discontinuities probably require a small amount of melt. Here's some other really interesting evidence for melt. Now I'm looking at SKS splitting results, which reflect the fabrics in the crust and mantle, these mostly the mantle. You can see in the East Pacific rise, what the melt experiment observed were these directions that are very similar to the spreading direction and the plate motion direction. That's what you typically think of happening if it's caused by the alignment of olivine owing to the shearing related to the motion of the plate over the mantle. So that's great. That's what's seen there, and they're relatively muted in magnitude and mostly in the same direction. So that's great. When we look at what we see, it's much different. We see directions that are mostly in the plate spreading direction, but not always. You might expect that given the kind of complex mantle structures I showed you. So that's probably why these are so muted and also not always in the spreading direction. Whereas when we go to the ridge axis here, I'm just sorting them in color based on what's been predicted by numerical models for the scale of anisotropy. And the scale is usually like around 1 or 1.5 seconds. And those are the ones that are in blue here. But when we go to these observations, which are much greater than that, these cannot be explained by that classic model. If you look at the Blackman and Kendall modeling of anisotropy expected at a mid-ocean ridge. These are really large, and they're mostly near the ridge axis. And they're also, many of them are ridge parallel. So that was really interesting to us. Given that they can't be explained by olivine, a more likely scenario is that there's some amount of partial melt, and that it is aligned parallel to the ridge axis. And how exactly you get that, that's a really interesting question. But when we considered this, by looking at the shear velocities from surface waves again, you can see that in the East Pacific rise on the bottom, we observe velocity contours that are relatively horizontal. So motions, plate motion stresses and strains are likely going to result in these olivine alignment. Whereas if any melt is aligned there, it's probably in a more horizontal fashion, and horizontal melt layers are not going to give you this directional azimuthal anisotropy. Whereas if we look at this is the northern segment here, you can see that the Atlantic is a much different structure in terms of shear velocities. We have these very steep margins, and those steep margins likely facilitate the organization and alignment of melt in vertical structures. And the other interesting thing about this is that melt is predicted to be relatively buoyant. And it happens that the Atlantic actually the mid-Atlantic ridge sits higher above surrounding ocean lithosphere in comparison to the Pacific. So it could be that this buoyancy is actually pushing the ridge up. And that, so given that the Atlantic, we know that the Pacific is driven primarily by the gravity pulling slabs at subduction zones, but the Atlantic is not surrounded by this massive ring of fire system. And so it could be that these kind of ridge, this buoyancy beneath the ridge axis is playing a larger role in comparison to the Pacific in driving the plates. And it may also play a role in decoupling the lithosphere from the asthenosphere. Okay, so bringing it all together, we see that the lithosphere thickens with age, but not always monotonically. We have this evidence for a lithospheric drip. There are some locations where we have a relatively simple age progression and a relatively gradual drop off in resistivity and velocities with depth. We also have evidence for punctuated anomalies several hundreds of kilometers off the ridge axis. In this location, we likely require a gradual drop off with depth. That's why we are able to image this receiver function phase. We also have evidence for this channel feature, which is not well imaged, for instance, by receiver functions. Okay, so these punctuated anomalies are similar to what's been predicted by geodynamic modeling. These are the classic Richter rolls that are predicted particularly beneath slower spreading centers. But what's interesting is that our anomalies are not with the same kind of symmetry as the Richter rolls, which are obviously have a ridge perpendicular symmetry. Instead, we have these things that are kind of going off the axis in the opposite sense. Exactly why that is, it's not known, but it could be because we have these large offset transforms, both at chain and then also at Romanche, that are giving these kind of instabilities, owing to lithosphere of a younger age being juxtaposed with lithosphere of a much younger age. It could also be that they are just not very well developed because it's a relatively young age lithosphere. Okay, so bringing it all together, we have likely have melt, hydrated melt. We see it in a thin channel and in thicker channels with a gradual drop off, and also in punctuated anomalies. If melt is there and these percentages we require, it likely defines the plate. And that suggests that the lithosphere-asthenosphere boundary is determined by melt generation and migration, and it may be laterally variable and temporally variable. And what's interesting is that because we've imaged this melt in a variety of ways, all in a single location, it suggests that the many forms of melt that have been proposed globally could all be the case. They need not actually be an artifact of resolution. And we kind of reconcile these different forms. This is a compilation of many different forms of melt. For instance, the large melt triangle from the melt experiment, melt in very thin channel structures, melt in layered structures, these punctuated anomalies from our study, the very thin MT conductivity anomaly, and then the melt matrices from geodynamic modeling. Okay, so I already mentioned the effect that the melt would have in terms of affecting mantle dynamics via buoyancy forces and also decoupling. And so we'd like to know a lot more about this melt with more imaging in the future. And this is also true in subduction zones where melt has been proposed in a variety of forms, like very, very large structures, thin conductive layers, in multiple layered structures, and in very thin melt channels. So what's interesting is that this work is also supported by geodynamic modeling, including two-phase flow. These studies find porosity waves, which are ephemeral melt-rich pockets that form owing to viscous resistance to compaction and decompaction of the solid mantle flow. And you can see the prediction for a slower spreading center on the top here is that you might get these, and they would kind of, they pond beneath the permeability boundary, like the LAB, and they may accumulate for some time. And then at some point, they also end up freezing back into the lithosphere and also sometimes vacating the system altogether via the ridge axis, and are later replenished at another time. So this is also consistent with our idea that you might have variable structures in time and space. Okay, so just putting this now into a global perspective, the LAB from the south I showed you there is this beautiful array of blue diamonds that fit really nicely into the global compilations. So that's really exciting. This is some other global work that we did. We just took phase velocities from Ekström 2011 and performed clustering analysis that's shown in the bottom. And you can see that just clustering these, we found you can easily pick out things that look pretty close to the tectonic regimes from the crust 1.0 regionalization on the top without very much work at all. And that's good. It means that temperature plays a first order role in really dictating that lithosphere-asthenosphere thickness. And you can also see that, these also this very, very gradual and predicted variation in age as you move from younger towards the oldest lithosphere in terms of 1D seismic velocities. Okay, now I'm just showing you averages. This is the SEMUM2 model. I'm showing you averages through all cratons in pink, and then oceanic lithosphere in cyan, and Phanerozoic lithosphere in green. And then I'm showing you all of the 1D profiles that went into that average. And you can see that while there's this very beautiful grade age progression on average, the variability within any one of these bins is very high. That's shown by the gray lines in the background. And I'm also comparing to a bunch of other measurements, which I'm not going to talk about today. Okay, so in synthesis, we have this very simple monotonic progression of lithosphere-asthenosphere boundary when we consider it in terms of age bins. And this is also true in the prevailing view is that there's kind of this very, very gradual change in lithospheric thickness. It's very thick in continental interiors with a gradual transition. This is based on the work of Johan and Romanowitz from the continental US. And that's pretty much what the prevailing view is. But when we consider single transects, this is through the same model, a single transect, you can see there's much more variability. We have punctuated anomalies. And whether or not that's a matter of resolution or not is something that's not discussed very much. But our results suggest that it could be the case that you have such variability. And it's also interesting to me because there's a view from the continents from geochemistry, which suggests that you might have a much more corrugated lithospheric plate. So that's really interesting and is very similar to kind of this idea that you have more complex topography. Okay, and I guess what was interesting to me is also there's kind of this debate about half-space cooling versus plate model. Classically, basically you have these global tomography models that show this thickening to the oldest ages that's more consistent with half-space cooling. Whereas, there's also these observations from heat flow and also bathymetry back since the 70s where they've said, well, actually, it's more like a plate model where you have, muted thickening of the oldest lithosphere. And there's some also surface waves that indicate that. And that's interesting to me because it means that both can be the case. If you're fitting the same phase velocities, it means that both of these shear models fit the data probably just as well. And that's interesting. The other really interesting thing is that this transect here, where you have the kind of continued thickening to the oldest ages, is the same transect I was showing in the last slide. So this one over here with the very punctuated anomaly. So this suggests that you can really have these very different structures, and that's good to know. Okay, so now talking about some of the other global compilations. Here, we compiled shear wave velocities from surface waves. They're shown, this is a model of Eric Debye. It's shown in the background here, colors. And these are all aged averaged bins. And what we're comparing them to is the estimated LAB. Most models we're typically assuming from surface waves and also heat flow, we're looking at the 1300 degree isotherm, which is a typical proxy. That's shown in black here for the surface waves. And we're also comparing to the predicted half-space cooling model. I have the 11 and the 1300 degree isotherm in red. And that's a plate model. And then the half-space cooling model in gray for 1100 and 1300 degrees. And then I'm also comparing to averages from scattered waves shown in white, averages from MT, magnetotellurics, in gray, and then also the depths of the mildly hydrated solid eye, 125 and 500 ppm. We're also showing some results from petrology beneath Phanerozoic and Archean lithosphere. And basically what you see is that the thickness of the lithosphere increases with age. That's true beneath the oceans, and it's also true beneath Phanerozoic, Proterozoic, and Archean lithosphere as you go to older ages. That's good. Again, temperature is playing a first order role. What's really interesting is that these depths are relatively shallow. I don't know if you can see it, but they kind of break from the half-space cooling model at an earlier age in general than we typically think. We typically think of them breaking at around 70 million years. They definitely break earlier. They're also, a lot of them, more consistent with they're consistent with the plate model, which is good. But then we're using a pretty thin plate model here. It's also thinner than the typical paradigm in the textbooks and literature. It's a 90 kilometer thick plate. And they're also some of them are relatively shallow in comparison to that. Something like closer to like the 1100 degree isotherm. So that was also interesting to us. And I guess the other thing I want to say about that is, well, why is that? Why are we slightly different? Well, we've talked a lot about how, surface waves can accept a wide range of models. And so the agreement that we have between our methodologies is really suggesting that, this shallower kind of plate model is more likely. So that's interesting. The other thing is that beneath the continents, in the literature, there's a focus on the thickest lithosphere, like 200, 250 kilometers depth. And then that's usually in schematics applied to the entire interior of the continental regions. However, those depths are only reached in 1 or 2 pixels of these models. For instance, from heat flow, and actually seismic tomography doesn't really even get that thick. It's mostly around 200. It gets to just 200, 240, but it's mostly there's really, really small percentages that are actually at the higher end of this blue area. And heat flow does get deeper, but it's in these very discrete areas. And one reason that can be is the heat flow is a relatively smooth model, and then the radiogenic heat production that's applied to that model uses the very sharp Crust 1.0 model. And this can artificially give you deep LAB depths in various regions at the edges of that Crust 1.0 model. So that's also quite interesting to me. And the other thing is that these blue or regions with a deeper lithosphere occur over much more discrete areas than, for instance, the Archean lithosphere of the S3MAC model. But overall, you can see the general global agreement, which is actually quite good from scattered waves, heat flow, and seismic tomography. Okay, so in conclusion, temperature plays a first order role in dictating LAB depths, but we have shallower depths beneath old ocean lithosphere and also continental lithosphere. This suggests that either we have higher mantle potential temperatures or there's a solidus definition to the LAB. And in other words, other factors are required besides the typical thermal model. And then we have these variable LAB depths, which also require more dynamics. Okay, so yeah, that's all I wanted to say about that exact topic. But I also, before I kind of end, I just wanted to talk about a few other things that I'm working on in case you want to connect with me about any of these other things that I'm doing, because this is, this is work that's ongoing, but just so Okay, so we also did a bunch of seismicity work in this region. We found that in these areas, we have these areas where we have lots of, where there are pop-up structures that have been formed by compressional forces, and there's lots of deformation of the surface, overlapping faults. And where we have those structures, that's shown by the blue areas here, we find that we have deeper earthquakes and also that they're very, very small earthquakes, whereas the areas in between these regions, we have big earthquakes and they're not very deep. And so our hypothesis is that in these areas with the deformation, more hydration is getting into the lithosphere. And you can see this in the active source image up here. This is one of the big flower structures, and you can see there's slower velocities at shallow depths. That's probably because of serpentinization. And then as you go to deeper depths, we actually have the faster velocities extending to deeper depths. So basically we show that we don't really need a very special mechanism to explain these deep earthquakes, because we see fast velocities at deep depths. So the 600-degree isotherm is kind of brought down by this hydrothermal cooling, and resulting in kind of lots of small earthquakes. So they're kind of these barrier regions in comparison to the intermittent asperity regions. We also have evidence for tidal triggering in the north. We had a station that was right on the ridge. And this is quite interesting because it's not really expected given the stresses. And so the most likely hypothesis is that there's a magma chamber beneath it. We also were lucky enough to image this super shear earthquake on the Romanche transform. It was in magnitude 7 and had a very interesting source rupture pattern. We've also been looking at the depths of petrological melting in comparison to our velocities. And we also had 2 other large field experiments in the past few years. There was 10 land stations and 34 ocean bottom seismometers deployed in the Lesser Antilles, where we found evidence for interesting and unexpected fluid migration, where fluids are coming off the slab and then traveling above the slab towards the back arc region before rising to the base of the plate and then ponding before coming back to the arc. We think this might be happening in other subductions as well, but because of our extreme situation with the slow spreading in the Atlantic, it might be happening in a bigger way here. We also had 25 stations deployed across Papua New Guinea, and this was in collaboration with 25 ocean bottom seismometer stations across the Antan-Java Plateau to study the large igneous province there. Oh, the 25 ocean bottom seismometers were from the Japanese. Okay. The other thing I've been doing is looking at rapid deployments of DOS, or distributed acoustic sensing. These are typically people use cables that are already existing, but sometimes you want to put something out quite quickly, for instance, to monitor various migrations. It can also be used for places like the moon and icy planets. So I've been working with engineers to develop better interrogators and also ways of coupling these cables to the floor, to the earth rapidly. And then also looking at using different kinds of cables, like including wind farm cables, given that we likely have more wind farms in the future. Okay, I've also been looking at the transition zone. This is some work in the Lesser Antilles where we showed that there's this really super deep 660, and the only way to explain it is by this a huge amount of basalt content. And what's interesting is that this occurs in the exact location where there's an extinct ridge. So we think that a large amount of basalt may have accumulated owing to the kind of failure of that ridge. And then in the Cascadia, we've also been looking at the transition zone where we find evidence of unexpected flows where the upper mantle convection, as suggested by the body wave tomography, is dictating where material enters the upper mantle in comparison to upwellings from below. And then this is like the kind of one really big thing that I'm excited about right now, and that's doing joint solid earth oceanographic investigations. So basically the oceanographers want this information about the water column, and geophysicists would like to know this information about the mantle. And we use signals that are contaminated one way and the other way. So the reason that the oceanographers are studying the oceans is because they think, for instance, that the AMOC, or the Atlantic, large-scale Atlantic currents are slowing, and then that will in the future result in extreme climate conditions. But the amount that it's slowing is discrepant between study locations. And so it's really important to get this right. However, these studies do not account for changes in solid Earth motions, even though in some places they are located in places where the Earth is moving. And then the other thing is, the other reason to do this is because most megathrust earthquakes occur at plate boundaries that are located offshore, and geodesy has transformed our understanding of Earth motions on land, but it's been very difficult to do beneath the water because the satellite signals cannot penetrate the water. However, there are these new very high precision AZA pressure gauges, which we can use to look at vertical seafloor motions and assess the likelihood that there, the amount of energy that's being released via slower events and earthquakes, and assess whether like the likelihood of a large megathrust. And so doing these together with the oceanographers, we can use that ocean column data to do a better job with our geodesy work or our seismicity work, and vice versa. And this is not, I am doing some studies now in the Bahamas, where we don't expect plate motions, and also in the Lesser Antilles where we do. But this is a much bigger thing that I hope many more people will get involved in, because the oceans are really the final frontier of seismic imaging. They're really important also for things like megathrusts. So I hope that we get much more large-scale deployments of including smart cables that can bring this information back to us. And it's going to be it has to be a much bigger global effort, since this is not something that's typically funded, in a large scale by the typical mechanisms. Okay, thanks very much.
Hey, Kate, thank you for a very comprehensive talk. And now it's a Q&A session. And for the first two questions, we can start from the students and our postdocs.
I ask a question. Hi, thank you so much for a really great talk. I was wondering about your joint inversion with the MT and the seismic. Is it iterative, or is it just you have the starting model from the MT and it goes straight into the seismic model?
That is a good question. I do not think it is iterative. I did not do that inversion.
Okay.
I can try that.
Thanks, that was a really great talk. I was wondering, in your global compilations, there seemed to be a break at 100 million years.
This one?
Yeah, and
Okay.
I was wondering if you could say why that is.
Can you describe what do you mean there's a break at 100?
There's a smaller VS anomaly compared with it's a lighter color.
Oh, like this, okay, so this right here.
Yeah.
Oh, okay. Yeah, that's interesting. We were kind of just pleased that overall it was there was kind of this this gradual, very nice relationship. I had never noticed that, and I do not know.
You're okay. This is Thorsten. I think that's Hawaii. So when you look globally, you're going to be biased by the Pacific, and that's where you see it clearly. And I think if you had restricted it to Atlantic, you wouldn't get that.
Interesting. I love it. Thanks.
Hi, thank you for your talk. I really enjoyed it. And I'm actually wondering about the possible relationship between the bottom of the lithosphere and the oceanic earthquakes, because you mentioned that at a depth of maybe 60 or 80 kilometers, there could be additional dehydration or hydration and then dehydration that can cause earthquakes at around 600 degree isotherm. But actually, in our study, we have found that for intermediate depths and deep earthquakes, that the earthquake rupture can extend this 600 Celsius degree isotherm. So I'm thinking about it's possible that other mechanisms, such like shear thermal instability, could play a role. Do you think it could also play a role in deeper lithospheric earthquakes in the ocean?
Yeah, so I mean, I know what you're talking about. I guess what I would say, oh wait, that was the other way, sorry. What I would say is that I know that other people have proposed these kinds of different mechanisms. I just don't think we need it, because we had the shear velocities, from the surface waves, and we were able, a lot of these studies don't have this kind of deep imaging of the mantle, and we were able to translate those to expected temperatures. And you can see here that, when the 600 degree isotherm from half space cooling is in blue, but when we translated the velocities to temperatures, surface waves have this broad sensitivity anyway. So, but the idea is that in general that like the 600 is actually quite deep, but then like also that this 100, you can see that it's generally faster to deeper depths in these kind of two areas, and that's what gives you these kind of, I think that's what's explaining our results. So we just don't necessarily need anything different besides the 600-degree isotherm. Yeah, I mean, I know that 600 degrees, many people are saying like that it's kind of like everybody's kind of going for that number, but it's just in our case, we just didn't need it. And we're lucky to have this imaging that we can say that,
Thank you.
Thanks.
Thanks, Kate. I hope you're feeling better. And I wonder, given that you have this neat high resolution sampling as a function of seafloor age across the transform fault, if you took it further than what you've shown here in the sense of linking it with the sorts of thermomechanical models that Mark Bain and Laurent Motesi have built, because you showed this slide where you have like these super nice receiver functions, age progression, and then you see the transform offset. And given all the constraints you have, did you sort of bring it into a mechanical model?
Not yet.
Right. And I'm asking, right, because so there are sort of subtle differences in the predictions of temperature and apparent age, depending on what you do with the faults, right? And so looking at the slides you're showing right now, so there's sort of this idea, there's temperature control and seismicity, but then there's a bit of a frictional plastic control. And Mark Bain explored that in a bunch of models, and he used focal mechanisms as constraints, right? Transform faults are weak, blah, blah, blah. But what you have is like more comprehensive, and you could actually convert, as you've done, right? All of your seismological and EM constraints to an apparent age and see sort of how it works out combined with the mechanical stuff, is what I'm saying.
Yes. So we have done some things like that, because when we're trying to match the seismic the shear wave velocities from surface waves to the petrologic depths, we had to kind of take like a half space model and say what age we think it was. So like, I guess we're on that track. I mean, like, it's like, I mean, obviously, like, we want to get together with the modeler and do more of that. But yes, like, so we started to do that when we were working with the petrologists. But that's kind of work in progress that I don't have anything to show today.
Yeah, cool. I mean, it doesn't have to be complicated, right? But people have these sort of 3D transform off the set things. People love to model it. And you could sort of just look at your depth of receiver functions and put it next to one of Mark's or Laurent's sort of predictions and see if there's sort of a second order agreement or not, and what that might be telling us.
Yeah, thanks.
Okay, so I have another probably last question. If there is no, and so Kat, you trying to use surface wave, body wave, and have you tried to use the full waveform applied to the OBS stations, and what you found?
Good question. Yeah, so we were really excited to do full waveform inversion, especially because of the complexity in this region. Some people have said, given that, really we shouldn't trust anything, right? But I trust it because we have good agreement. So Yu Jiangji worked for us for the past many years, and that is one of his tasks. And he ended up doing other tasks during that time. So I don't have a result yet, but one really challenging part of that so far was working in the Lesser. So he's working on both the Lesser Antilles and HiLab. Lesser Antilles is a lot more complicated because you need to mesh land and water. And so that took a lot of work, but we finally got that going. And we have like a huge amount of computational time, but it's just a matter of Yu Jiang having time to do it. Actually, Yu Jiang is actually there at Texas, so maybe he can give you an update. But yeah, it's really exciting work, and I'm excited to see how it comes out.
Cool. So any more questions?
Hi, Kate. It's Eric. Excellent talk. Thank you. The you said that the empty lab, that was kind of surprising how it resolved the LAB, but also kind of troubling in my view how the bathymetry coincidentally goes with that bathymetry on the east side. And I know that Xiangwang used a determined inversion for that. It's kind of a workaround the 2D because that's a complex area. Easy extended it to a 3D kind of model in order to resolve that and see that kind of a good agreement between the bathymetry and the thin LAB, because that's amazing that we can solve such a thin LAB with MT. And the synthetic test that he has done, that shows that we can resolve something. But you know, it's kind of also whatever you feed in, it will have the ability to solve that. But it's still I'm not fully convinced, I would say, on that thin LAB. So
Oh, you mean this, like the thin channel?
yeah, you can see the coordinates, and even in the synthetic that it does, there is some features over there that are obviously artifacts, and the determinant is it's a redundant 2D in order to resolve that. Yeah, so you have those two big resistors and a conductor between them before the LAB. I'm just wondering if Xianggu extended it to 3D.
Yeah, so that's what he's doing right now. During he has a fellowship in Oslo, and that's exactly what he's doing. Yeah. But he's developing this 3D code, which is taking some time. Yeah.
Any question online? No? Okay. If that is all, so thank you, Kate, again for the great talk.
Thanks very much.
Thank you all for coming.